Yes, mic's on. So the question is, and this is multiple choice, right? So this is from exam of 2018 February, so February, March, paper 1, right? And we're given that a small stone is dropped from a certain height, y, and somewhere there that's the ground. All right, so we are told to assume that upwards is positive, and after some time the stone hits the ground after time t. So after time t, the stone hits the ground and it's shown in the diagram. So which one of the following diagrams shows the correct position time graph for the motion of the stone? Right, so it's a multiple choice question. We're given 4 different graphs, and these graphs illustrate the relationship between time on the horizontal axis and position on the vertical axis, right? And we're also told that we should regard upwards as positive. Yeah, and then we can ignore the effects of air resistance. So, using our knowledge of science, rather the one-dimensional vertical projectile motion, yes, that chapter. We need to then look at a displacement, or rather position time. So position has to do with displacement, etc. Right? And in the exam, what we must show is this stone as it falls, which graph? Is it the straight one? Is it the curved one like that? Is it the circular one like that? Or is it a straight one like that? So we need to find the correct one here and select it, right? That's one way that these types of questions for one dimension vertical projectile motion can manifest. So I'm learning so much. Anyway, so so we must first I think we must look at displacement time graphs, because position would have to do with displacement, right? And when we do that, we can analyze the motion of the stone. Yeah. We're first told that as the stone is just dropped. So someone's hand was holding it, and then they let it go. And when they let it go, it started dropping. So as it drops, it's subjected to a number of things, right? It starts off at V0, at V initial. At V initial equals 0 meters per second. And then it's dropped. And from there on, it is subjected to the acceleration due to gravity of 9.8 meters per second squared. Alright? Right up until it hits the ground at the end of time t. Okay, so on each of these graphs, we do have an indication of time. It's on the horizontal axis. And we know that any one of these could be correct, because these are examples of graphs where for a stationary object, a straight line moving from displacement x all the way into to the right like that would be the first block on the top left. If the object is in uniform motion, then it will be a straight line, but that's at an angle. And if it's in constant acceleration, it will be a curve like that. But now, our so we need to select the correct graph that represents the motion of the stone. The one number D, ne?
It's a gradual drop. I'm joking, yeah?
It is a drop, but something is gradual. What do you think is? What is gradual? What is gradual? What do you think is gradual?
The should I say the velocity?
I would say it's accelerating.
Okay.
Because it's subjected to acceleration due to gravity.
Yeah.
Meaning its velocity changes. Acceleration means a change in velocity over time.
Yes.
Yeah, so perhaps it's under a constant acceleration, perhaps it's under something else. Okay, the ground is zero reference. So if the ground is zero reference, it means that we count the height going from the ground all the way to the top. So at the top, that's y. Yo.
Hello?
Yeah, I'm here.
Oh.
I'm here. Don't right, cool. So in our answer, because it's 1.3, ne? In our answer, it is number C. This one here.
Awkward.
Now we're gonna try and explain why C. Okay, so we know that the position is measured from the ground going up. So from the ground going up, meaning on the ground level, the y is 0. You get? So any one of the graphs of the 4 graphs where the position goes from y to 0 might be correct. And now that's 3 graphs. Right? It's this one, it's that one, and it's the straight line. Alright. So all of these 3 graphs, because we know the position drops, each of these 3 graphs might be correct. So that eliminates D. That eliminates D because there's no change in position. It's a stationary object. It should be stationary at height y, but it's not. It's being dropped. So this graph D does not represent the situation quite well. So we're left with 3 options. Now we've eliminated the 4th one. We're left with 3. Upwards is positive, ground is 0 reference, and stone hits the ground after time t. So all 3 of them, a certain amount of time passes, and after it passes, only then do we get the change in the vertical drop. So only then when the time changes over a certain time do we get a drop. So from height y to 0 on the ground. Now we need to study our graphs quite well. First, looking at the straight line graph. The straight line graph is usually attributed to uniform motion. Uniform.
What example do you make of something that is uniform motion? Would it be an aircraft once it's reached the desired altitude?
Yeah, at cruising speed, so it's a constant speed.
Okay.
Yeah.
Okay.
So in other words, it's no longer accelerating.
Yeah.
It's not accelerating.
Yeah.
So this first graph we can eliminate because of that. Simply because uniform motion, like straight line like that, would simply mean there's no acceleration, and that is incorrect because there is an acceleration.
Like a feather.
Like a feather, yeah.
Yeah.
So a feather it's too light to be affected by acceleration due to gravity, so it just waltzes down to the ground. So we've eliminated straight line graph. Yippee.
And the horizontal graph.
And the horizontal graph. So now we're left with just two graphs. That's B and C.
Yeah.
So graph B is hyperbolic. Not that that's a big deal, but let's look at what the curvature communicates to us. Okay, so on our learning guide from pages 85 onward, right? On our learning guide from pages 85 onward. So in your search bar, just type there 98 or 98. Yeah, so it should take you to page 86 and then, or rather 89, yeah. So when we look at those two graphs, the initial velocity in the description of the motion, we did agree that the initial velocity is 0. And that's at the point where the hand that held the stone is just letting go of the stone. So the velocity is 0. It starts out as 0. Now, when you look at the position relative to the time taken, can you see that on the graphs on page 87, velocity starts out at 0, and the equation of motion that governs this is the displacement vector is initial position plus velocity initial times the time plus a half times acceleration due to gravity times time squared. And from math, we know that when we have an exponent for one of the variables, in this case our variable is t. T is the one we can vary, and it has a particular relationship with the position either y or x. In this case, position y, we would say that's what was supposed to be used in the case of position x for this equation. But the point that I'm illustrating is that Just like in math, where if you have x and y like that, a parabolic shape is something like that. So this is also a parabolic shape, and also because a parabolic shape is described by ax squared plus bx plus c, or a into x minus p all squared plus q, right? So that explains a parabolic shape, just as this explains a parabolic shape. So in other words, the best possible answer here is indeed C. And it is C because we know that the position displacement relationship is a parabolic relationship. And that's on page 87 of our learning guide. And that's what gives us the correct answer, C. So we get 2 marks for that. But that's what we should remember, that the relationship between position and time is parabolic. So we look for the parabolic relationship. I mentioned that graph B, which was like this, is hyperbolic. And I said that's not a big deal. It actually is a big deal because the relationships for hyperbolic curves are xy equals k, and when you make y the subject of the formula, it's just k over x. And the graphs typically look something like that, where the x-axis and the y-axis are asymptotes, and you can also do horizontal and vertical shifts, but we'll do that in math. So graph B falls off because it is hyperbolic. So the graph here is parabolic.
And you said graph A falls off because?
It implies uniform motion.
And graph D?
Graph D, it implies that the object is stationary.
Okay.
Yeah, so this is, so if it's position and time, then this implies stationary object. If it is this curve, then it implies velocity initial is 0. And if it is like that, then it means, okay, but here the object was dropped. But if it is like this, if the graph is like this, v initial is not. However, this implies uniform motion. So uniform velocity.
I want to change my answer to A.
No. Yeah, but the correct answer is C. So, yeah, but I get why you would think, because if it's accelerating due to gravity, it's easy to think that it's uniform motion. But the motion in this case, we refer mostly to the velocity, not just the motion loosely like that. And then the other multiple choice questions, we'll do as and when we get into those parts of the question of the content. Yeah.
You're in March, they already have so much.
Yeah. You can imagine, because it's such a big deal, getting this part of schooling right for a lot of people. A lot of people are hinging.
I thought this would have been a revision paper.
Oh, yeah. But it's also a good way to reflect on how far one has grasped the concept so far. And the nice thing about it is that it already has a lot of the stuff that we ought to have captured, or at least learned for paper 1. And it sets the tone for the rest of the year. Yeah. So, but it's always a good reflection, the fact that it's written in February, March, it's always a good way to check yourself against what ought to have been learned. So we know that we are a bit behind on this stuff. So we will have to ramp up our pace. That's fine, we'll do that. But anyway, question 3 is 1D vertical motion. And we have a graph like that, right? Right, and in our graph, a ball is thrown vertically downwards from the top of a building. And then it bounces a few times as it hits the ground. Just by looking at the graph, if I may ask, Nobuti, can you see where it bounces and like where it bounces and where it's
It bounces at
2 seconds?
Yeah, which is when it reaches 0.
Okay. And then I think it drops.
Because 0 is not a base, it drops.
It drops at
to negative 25.
to negative 25. I don't think that's correct. Remember, we think about our, so vertically downwards is positive, right?
My 2.2 seconds.
Eh?
I'm sticking to my 2.2 seconds.
2.2 seconds, okay. The correct way to think about this, ne? Firstly, our convention is that the ball is falling vertically downwards from the top of a building and bounces a few times as it hits the ground. So the velocity time graph describes the motion of the ball from the time it is thrown up to a certain time t. So how you can think about this, the best way to think about this is that now it's thrown, right? It's not dropped, it's thrown. So if it is thrown, it has an initial velocity that is not 0. That's the first clue. And then it accelerates, yeah.
And then at some point it reaches a 0, and then there's a fall.
So now that it's been thrown and it's falling, when it smacks the ground, it touches the ground for some time, a fraction of a second. It kisses the ground for a fraction of a second, and then it bounces. So if vertically downwards is positive because the velocity in this graph, so on the Jamboard, just look at the Jamboard quick.
Yeah.
So the velocity, because it's thrown, starts somewhere at 10 meters per second.
Yeah.
Right? So at 10 meters per second, it is thrown. And then it falls because we see that because it increases in velocity, meaning it accelerates. Right? Meaning it accelerates. Now after accelerating, it smacks the ground at 2 seconds. And then when it smacks the ground, it kisses the ground for like a fraction of a second. Can you see where that happens?
Yes.
Where's that?
At 2.2 seconds.
So between 2 seconds and 2.2 seconds, that space there, that's when it kisses the ground, yeah. So if we were to visualize the motion of the ball, this is the floor here, right? It's thrown from the top of a building, and as it's thrown, it drops all the way, and then this point here, that's when it drops.
Yeah.
And kisses the floor. Now after that 0.2 seconds, After that 0.2 seconds, the ball... Oh yeah, another thing I wanted to point out was that since vertically downward is the direction it's thrown, the acceleration vector, which is acceleration due to gravity, and the direction of the velocity are positive. That is what we see on this part here of the graph. Right? And also when the ball now bounces again, we see that with the vertical, or rather the diagonal line, that spikes up like that again. So that spike shows us the bouncing motion.
Is it a gravity acceleration motion?
Okay, so we need to first think about how... I like that question. Is it a gravity acceleration motion? It is subjected to acceleration due to gravity, no doubt, the ball, because naturally that's what would happen, right? But I want us to think of the correlation between these points here. Right. So when the ball smacks the floor at 2 seconds, and then it kisses it for 0.2 seconds, it touches the floor for 0.2 seconds, it then proceeds to bounce up again. So now it changes direction from down is positive to up is negative. Right? And that happens when... Yeah, that happens right after the first bounce. The ball changes from moving in a negative direction to going up again.
Moves in a positive direction to going up again.
Yes. And that's where it coincides at 4.955 seconds. So, you know when a ball bounces, right? It hits the floor and then it comes back to a certain height. Now that height might not necessarily be the initial height, but it is a height where the velocity is 0. And it changes direction so that it can drop, so that it can bounce again.
And if it's not dropped at a certain force, which wasn't that Newton? What is force again?
So force is mass times acceleration.
Mass times acceleration.
Yes.
Okay.
So we're not really thinking about forces at this stage, but we're thinking about velocity, how fast the object is moving as it drops, as well as its interaction with the floor as it bounces several times until it stops at time t. So for this graph, that's what we are looking at. Yeah. So, but yeah, let's roll back the tape, right? So someone throws the ball from a certain height on a building. Please, for now, just open Jamboard.
I'm on Jamboard.
You're on Jamboard. Awesome. So the ball falls at an initial velocity. So between 0 and 2 seconds, right?
Yeah.
Ball falls at an initial velocity of 10 meters per second. And it is subjected to acceleration due to gravity. And up until it hits the floor, right? We see that the velocity also increases right up to when it hits the floor to 29.6 meters per second. Yeah. So meaning from when it's dropped all the way to when it falls, the velocity increases. And when it reaches its maximum velocity, that's when the ball hits the floor, comes into contact with the floor for 0.2 seconds, and then bounces back up.
Yeah.
So as it bounces back up, there's a certain point above here. You know when you're playing with a tennis ball and you smack it against the floor, and then it reaches a certain height. Like if say you smack it so hard against the floor, it bounces to a height that, let's say it goes above your body height, even with your arms stretched out. Let's say it goes that high. But you can see it because it's not like into the sky, it's just above you, but it's not within reach, right? So when you're looking at that ball, try to imagine the ball, how it moves. So from the bounce, it reaches a certain height, stops going up, then turns and falls back down.
Yeah.
So when it stops moving up, that's this point here at 4.49 seconds. It's 4.955 seconds. That's when it changes direction from bouncing up to coming back down. And now we see that is true because as soon as it changes direction, the velocity increases from 0, which it was 0 when it was stopping going up, when it reached the peak of going up into the air. And now the velocity increases again to 27. Yes, I like that you see that now. So now you're getting the pattern, right?
Yeah.
Right. So now it's at 27 meters per second, and that is at 7.71 seconds. At time t equals 7.71 seconds. And then it comes into contact with the floor. The ball comes into contact with the floor for another fraction of the time, of a second, which is 8.00 minus 7.71 seconds. So that becomes 7. That becomes 10. Becomes 9. That becomes 10. So that's 9. So that's 2. So 0.29 seconds. Yes.
Yes, mathematically speaking.
Or is it 0.29? Yes, it is 0.29 because 0.3 would add to 0.7. Yeah, so it is 0.29 seconds.
Yeah.
Right, cool. So for 0.29 seconds, it's into contact with the floor. And then, so in the first instance, it was 0.2 seconds. In the second instance of the bounce against the floor, it's 0.29 seconds.
Its velocity is slower now.
Yes, now you can see. And as you can see, the velocity keeps dropping.
Yeah.
Can you see? The velocity keeps dropping.
Oh, it's negative.
You see? It keeps dropping. So here, on the negative, like in the direction where it starts moving up, which is the negative direction, the magnitude of velocity is negative 25 meters per second, which is less than the first bounce, which was at 27 meters per second. You see? Now at a certain point t, it's at 0. So that means it's up again, but not as high as in the other bounce, but it's bounced up, and we can also anticipate that it's going to come back down again. So we'll just put that there for reference in case you have to project there, right? And just another thing, it seems like there's a pattern. So the first velocity before the bounce was, the maximum was 29.6. And then there was the first bounce. So that means that should be less than 29.6 but it could be more than 27, but it's definitely more than 25. This part here, the velocity here at x, right? So the velocity at x should be less than 29.6, but it shouldn't be more than it shouldn't be, but it can't be less than, it should be more than 25 meters per second. Yeah, it should be more than 25 meters per second. So write down the speed with which the ball is thrown downwards. So now we've analyzed the motion. Now we can start answering questions. So 3.1, the speed with which the ball is thrown is 10 meters per second.
10 meters per second.
100%, because the graph tells us that information, right? Because the ball was thrown, it was not dropped, it was not let go of in air. So all the parts of the graph have the same gradient. Why do you think that is?
That it has the same gradient.
Yeah, all these lines that are blue on the Jamboard, see these diagonal lines that are blue? They all have the same gradient. So the change in y is the same as the change in x. Why do you think that is, if I may ask you?
Is it not acceleration from gravity?
Yes, it's the acceleration due to gravity, because the slope of the velocity time graph gives us ding 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 the acceleration due to gravity.
Yeah. Ding ding
Ding
ding.
ding ding. So I just put there g equals delta v over delta t, just to show that the change in velocity divided by change in time is the gradient. So when we answer that question, we will say that the gradient of velocity versus time graph is acceleration, and for this case,
can you not also say that the fall is like a free fall because there's no hindrance, so it's almost like it's constant?
I guess because they do say we can ignore the effects of friction, air friction. Yeah, so we can. Yeah. So the question, at least they did give us that specification, so we don't need to worry about that. Now we must calculate the height from which the ball is thrown.
Yeah.
So 3 point. So we've got initial velocity.
It's this one that we learned the other time. It's the displacement is equals to velocity initial and change in time plus a half gravity something squared.
Oh, okay. Are you talking about the one we used to answer the multiple choice question where we were eliminating graphs?
Yeah, determine the time when the ball will be at whatever. But then you showed me the formula, which is the displacement delta y is equals to velocity initial plus velocity initial time plus a half gravity squared.
Velocity initial. So it's the one with this position or displacement plus initial velocity times time plus half times acceleration due to gravity times time squared. Are you talking about that one?
Yes, times time squared, yeah. Is that not the right one?
We can test it out. We can test it out for sure, because I don't want to say no, it's incorrect. We can try it out because I'm helping you also explore how you can approach the question. So we're gonna say y dash is that plus v I t
it's
plus
delta y actually.
delta y. Oh, so it's this. Yes, it's this.
Yes.
Yeah, so that's delta y. And then when we take the y to this side with additive inverses, it gives us,
The velocity initial over time
it
plus
gives
a
us
half.
that.
Yeah. Squared. Yeah.
Yeah. All right. Cool. So we can use that. It's fine. We can use that. We know that initial velocity is 10, and so between 10 meters, which is at a certain height, yi,
You said it's times 2.
the time is 2 seconds. Yes,
Yeah.
2 seconds, definitely. Plus a half into 9.8
10.8
times 2 squared.
2 squared.
Yeah, so then y bar, so the second y should be 0,
Let me see that.
because the take downwards as the positive direction and the ground as 0 reference. So if the ground is 0 reference, then here we have a certain displacement,
Yeah.
y initial,
But why are you still using y initial?
because
we know it's 10 seconds.
oh, okay,
10
wait,
meters per second, sorry.
that's velocity, 10 meters per second. Yes. So our graph, that our equation that says delta y equals v I t plus half gt squared. That equation comes from this one. It's y minus yi equals v I t plus half gt squared. And now, because we are looking at motion where something is dropped from a certain height, and the height at the ground is 0, and that there is y, then we know that this here is 0 minus yi. So that's why in this instance, this I wrote it like that. Because I used additive.
So now that we've discovered what yi is, it would not form part of the equation on the right hand side.
Oh, no. It's still a part of it. It's just that because we've manipulated it, it's on the other side. It's still part of the same equation. It's just on the other side because we manipulated the equation. Nevertheless, so we have here we've got 20 plus that's 4 divided by 2 is 2 times 9.8 is 19.6 plus yi equals 0. 39.6 meters.
It can't fall 39.6 meters, but it can fall 39.6 meters per second.
Eh?
Was the question not looking at, okay, I can't see it now, but was it not looking at the velocity, which is expressed as meters per second?
Oh, no. For this particular part of the question, we're just looking at the height. So in other words, the drop. Yeah. In other words, the height from which it falls.
Yeah.
And then we must now find the time t shown on the graph. The time t shown on the graph, we will calculate by there are 5 ways to calculate that 39.6 meters, 5 different ways. Each of them is 3 marks.
I think, if you're saying it, I'm sure the second one would be, if it was a y and an x and y axis, we'll be looking at a negative connotation, right? That's what you said the other day.
Say that again.
We could look at it as like a negative 10 meters per second, but still use the same half times squared times delta time.
You mean for this equation over here?
Yeah, but wouldn't everything be in a negative connotation if we oh shit, there it is. I'm still looking at the Jamboard.
So yeah, this equation, remember we're taking downwards as positive.
Positive, yeah. So I'm saying if we're taking it as negative.
Or if you took downwards as negative, we would stick to the convention.
Okay.
We would stick to the convention, so downward would be negative. So then acceleration due to gravity would be negative.
Negative, yeah.
And the velocity initial would also be negative. But then whatever answer we get at the end will probably be different because the sign or something will have changed. You know what I'm saying? Yeah. So, but does that answer everything?
Yeah.
Okay, great.
9.8, 2.6, yeah, makes sense.
Okay, perfect.
My puppy is so needy. Let me calm down.
Shame.
He's sleeping. We can't go to sleep.
Okay, I'm just looking for those equations of motion so we can refer to them quick.
Man, I love science, bro.
It's nice, ne?
Yeah, damn, I regret.
Regret what? Don't regret.
Not doing it. Write down the time that the ball is in contact with the ground at the first bounce.
No. We've already done that when you analyze the thing. We first have to find out the time t on the graph, big capital T.
Yeah.
We need to find that. So how do we find it? We can use equations of motion. We've got several of them. We've got V final equals V initial plus acceleration due to gravity times time. We've got V final.
And then delta time will give us
or delta time will give us the seconds. Yes, definitely. So we can use this one. From the graph, we know that at time t, velocity final is 0.
0, yeah.
But the initial velocity is negative 25 meters per second. We know that the acceleration due to gravity is 9.8 meters, and t is what we're looking for. So then we do additive inverses, then the 25 comes to the left hand side of the equation, and we're left with 9.8 t. And then we divide by 9.8 and t equals, how much is that? 25 divided by 9.8.
25 divided by 9. 25, 9 goes twice or 3 times.
So it's like 2.55 seconds.
25 divided by 9.8. Yeah, 2.55 seconds.
Yes, but that's not the final answer.
Uko.
Because that is the time that the ball moves over here. Remember our sketch of the ball bouncing?
Yes.
2.55 seconds is this time here.
Oh, we need to add the 8.
Yes, excellent. We need to add the 8. Therefore, t is 8 seconds plus 2.55, which is 10.55 seconds.
10.55 seconds.
Yes. Then 3.4, 3.4.1. We've already answered that. What time was the ball in contact with the floor? It was, so we'll call this part between 2 seconds and 2.2 seconds the time of contact 1. So TC1.
2 seconds.
So 0.2 seconds. Remember that one.
Yeah.
And then the time at which the ball reaches its maximum height after the first bounce. Do you remember?
9.
Yes, that's the one. That's the one. T peak height and first bounce, it's 4.955 seconds. The time that the ball is in contact for 0.2 seconds, from 2 seconds to 2.2 seconds. I think it's better to write that part as well, because they didn't ask for the duration that they just said the time that the ball, so it's probably better to include from when to when. And now we must find the value of x.
Is it when the ball is at rest?
No.
When the ball is at its lowest in terms of bouncing. When it comes back down.
On the contrary, remember we're being asked questions about the first bounce here. So at the first...
So please go back to the question paper.
Okay, let's go back to the question paper. They say the value of x, which is here.
Yeah.
Which is here. Right? Remember during the bounce, the first bounce. During the first bounce, the ball is in contact with the floor for 0.2 seconds from 2 seconds.
Yeah. Yes.
And then it after having contact with the ground for 0.2 seconds, it jumps up to bounce and then go up. So it has a velocity there it leaves with.
Of 2 seconds. Yeah.
At 2.2 seconds, it leaves at a certain velocity.
Yeah.
It leaves at a certain velocity for about this amount of time. 4.955.
Jamboard is not updating.
It's not updating. Hey.
Sample 3.4.2. Please refresh. I'm enjoying this.
Enjoy. This is so cool. So I've gone back to slide number 2 on Jamboard.
Okay. Alright.
Yeah. And I've added a couple of things, right?
Yeah, I see the multiple bouncing of the ball till it reaches the tee.
Yes. So in this question, we're being asked. Remember that kid who was still in the other
This whole
classmate.
now, eh? They did a, where are you?
They didn't know, where are you?
The boy is in first or second year uni. That's ass.
And he was asking the kids.
Equally now.
Hey, that kid, yeah, the way he said you must ask. But anyway, so we're being asked here.
I've got a cab.
We're being asked. Let me be serious. Let me be serious. So we're being asked. We're being asked to identify a couple of things, right? The first one is there's a certain velocity that the ball leaves with from the ground so that it can reach that height where it stops going up and then changes direction and falls back down.
Yeah.
So that velocity is how much? Because we know that it's probably less than 29.6.
I'm just guesstimating because it's very low. It's 27-ish.
It could be 27, it could be a bit above it, but at least we know more or less we should be there.
Yeah.
One. So to answer 3.4.3, we know we're looking at something between 29.6 and 20 and 20, 27, 25. Yeah, we're looking at something between those numbers. Therefore, if that velocity is our V final, then for the first part of the drop, which is this part here,
Yeah.
who's the time of that not the drop, man, the bounce, that bounce, ne? The initial velocity is here at x sharp.
Yeah.
What is the time? The time is from 2.2 seconds to 4.955. So that difference,
Oh, okay, let me see.
you see.
So it should go in a negative.
So we should have 4.955
755 negative.
minus 2.2. The time cannot be negative because we
it's on a negative axis. Would the answer not be 27.55? Negative 27.55.
I would yeah, if that is the correct answer, I would very much mark it correct because you said it's negative 20 something point something something.
Yeah.
Yeah, so we take the time 4.955 and you subtract 2.2, so I'm assuming you've already done that. It's 2.755
Yeah.
seconds. And then we know that the initial velocity is 0. Sorry, the final velocity is 0. No, wait. Yes.
No.
Yes. Final velocity at 4.955 is 0.
0.
Ne? Here, just at that point there. So, then the VI is what we don't know. V initial, we don't know, and that's what we calculated. So, you used which equation? No.
Yeah.
So, which equation did you use?
I didn't use any equation. I just took the when it changes velocity from negative 25.
Okay.
And minus the time it takes to go up with the 2.2 to give me that 2.75, and then I added it to the 25 to get the x.
Hold up. You took which one? You took the 2.2 to 4.955, that difference there, that distance.
Yes.
And then what did you do with it?
And then I added it to the negative 25 to get the x.
Oh, no. That's not how we do it.
Okay.
Yeah, that's not how we do it. But at least you're thinking about it, so that's good. So we have to again visit our equations of motion. Right? And when we visit...
4.3.
Yeah, in 3.4.3.
The value of x.
Yes, because it's a velocity.
Okay.
So if you check slide 4 of our Jamboard, I've already put down there. So if you check...
Yeah, 2.755.
Yes, 2.755.
Wrong. Velocity initial plus g times. It should be plus 2.755. Okay, yeah.
No. Let's think about it this way. The velocity at this point here. Let's go to slide 2 that illustrates the graph and the bouncing part, right? Point X is here where I made a yellow circle. That's the velocity initial from when the bounce goes up into the sky where it changes direction. And we're only going to consider that part only. We're only going to consider that part of the motion. Alright? So we're going to look between these 2 points here.
Yeah.
The time difference is 2.755. I'm going to use all yellow for all of these.
Yes.
Yeah. So the time difference, which is on this axis, is 2.755, right? But the velocity changes from x to naught. Can you see that?
Yes. Yes.
Yeah, the velocity changes from x to naught. So at x the
velocity initial.
At x the velocity is v initial,
Gravity.
and at 4.955 seconds, this is the magnitude of the velocity, 0 meters per second.
Yes.
Now we've got the acceleration due to gravity, and we've got the time difference, 2.755. So we can work out VII, which is negative 9.8 times 2.755. And that should give us negative Barney times 9.8. So negative 26.999 meters per second. So it kind of makes sense. We know that it can't be more. It can't be more than the velocity that the ball smacked the floor with for the first time. And
I charted at 27.
Eh?
I would have been wrong. I'd have charted at negative 27.
27. Yeah, but that's because we don't just take the time difference and add it to the velocity. Those are two different dimensions.
Okay.
Yeah, time only has seconds to it. Velocity has the ratio of distance and time to it in its units, in its dimensions. So you see, you can't just add them back to back like that. They're two different things.
Okay.
It's like saying, now you're gonna add how long you traveled to how fast you traveled. Yeah, that doesn't...
I did travel. Oh yeah, 28 point, okay.
You see, so you can't directly add...
10 meters per hour, but it does not necessarily say how far I traveled.
Yes, you may travel at 100 kilometers per hour, but it doesn't necessarily say...
it took me 60 minutes to get there.
Yes. You see, it doesn't necessarily, because the dimensions are different. So up to there, you see how we approach exam questions with the same theory from our textbooks.
Sorry, I want to silence this. Sure. Focus.
Okay. Then the last part is the collision of the ball with the ground elastic or inelastic?
I would say because when you hit it to when it bounces, it's not the same. So it's sort of inelastic.
Yeah, the kinetic energies are not the same. You are definitely correct when you say they move different. It moves different at different times. So the speed at which it strikes and the speed at which it leaves the ground are not the same, meaning the kinetic energies are not the same. So V of striking is not the same as V of leaving.
Yeah.
Therefore, KE of striking is not the same as KE or kinetic energy of leaving. Therefore, it is inelastic. I like how you're grasping the concept, so thank you so much.